Hello, I'm Shigeo Takahashi. I'm going to present our recent work on visual analysis of geospatial multivariate data for investigating radioactive deposit processes. Before going into details, let me talk about my relationships with Professor Kunii. Actually, Professor Kunii was the research supervisor when I was the undergraduate student at the University of Tokyo and kindly continued his dedicated guidance during my PhD program. In the early stage of my research career, he led me to the research on shape description based on differential and algebraic topology, and thanks to his direction, I could successfully obtain my PhD degree and start my own research career as an individual researcher. One of my favorite publications shared with Professor Kunii is about the new algorithm for consistently extracting topological features from digital elevation data presented at the Graphics Conference in 1995. As you may know, he received a large number of the awards, including the IEEE Taylor Bose Education Award in 1998 and the Order of the Sacred Treasure in 2013. Another notable contribution of Professor Kunii is that he founded the University of Aizu, which we currently belong to, in 1993. This is the first university in Japan solely dedicated to computer science and engineering, and Professor Kunii served as the founding president. Thanks to his visionary design of this organization, UOA has been recognized as the unique and outstanding university in Japan, and it's gaining worldwide identification despite its short history. For example, UOA is incomparable, especially in Japan, since approximately 40% of faculty members are foreign nationals and now currently gets high praises in Times Higher rankings. UOA is located in Aizu Wakamatsu City, Fukushima, in the northern region of Japan. The city has been famous for its sense of history as a former castle town and is renowned for its high-quality Japanese sake products. As you may know, we recently had the great disaster in Fukushima region, the East Japan earthquake, and suffered from the associated nuclear power plant accident. Our university has made dedicated efforts to support the steady reconstruction of this region by taking advantage of expertise in computer science and engineering. This work can be thought of as one of them. Okay, let me start to talk about our research results. It has been more than 10 years since we had the March 2011 East Japan earthquake. It was one of the biggest disasters we ever had, in the sense that the ensuing great tsunami caused around 60,000 deaths and over 300,000 refugees. What made the disaster even worse is the Fukushima Daiichi nuclear power plant accident due to the loss of the power caused by the tsunami. The disaster caused meltdowns and hydrogen explosions in several units of the nuclear power plant and the release of the large amount of radioactive materials over the surrounding areas. The radioactive materials were widely spread from the nuclear power plant, and inhabitants needed to instantly leave their hometowns without fully taking care of their houses and belongings. Ever since, ongoing soil decontamination work has been conducted by removing the surface of the soil containing unwanted nuclide. This work successfully reduced the radioactive material to a safe level and shrunk the associated restricted residence region considerably as a result. This dedicated recovery from the earthquake's damage has allowed us to conduct a more intensive post-analysis of the spatiotemporal behavior of the ambient air dose rate. In particular, understanding the process of the radioactive deposition is important. This is because the associated air dose rate is not fully proportional to the distance from the nuclear power plant, but rather depends on the deposition process. For this purpose, we need to consider weather conditions such as wind and rain after an accident, topographic features such as high mountains, and categorization of the land use types such as urban or forest areas. The video on the right shows the simulated spatiotemporal behavior of the C-137 after the nuclear accident on March 11, 2011. Which finally led to the spatial distribution on the left. We can observe that radioactive materials can easily float and move in the air due to the influence of the wind and suddenly fall onto the ground if they encounter rain. It's possible that even in the area far away from the nuclear power plant, the air dose rate becomes relatively high due to the weather conditions. For example, like this way. The post-analysis of the spatiotemporal behavior of the ambient air dose rate is beneficial for promoting scientific understanding of radioactive deposition processes, helping inhabitants avoid unwanted radioactive exposures, and planning better environmental restoration measures to maximize the reduction of their radioactive levels. These are photos of several helicopters used in measuring the air dose rate. I was also able to observe the measurement process, which was conducted in the restricted areas at the time. In this study, we conducted airborne radiation monitoring to obtain the spatiotemporal distribution of the air dose rate, as mentioned earlier. Shortly after the nuclear power plant accident, a series of the airborne radiation monitoring runs were organized as the national project, and a helicopter with the measurement equipment was employed. The airborne monitoring recorded ground surface gamma ray radiation over a wide area, including mountainous regions that are difficult to approach from the ground. The helicopter was also equipped with the global positioning system receiver, facilitating the precision of the helicopter's positioning when measuring the air dose rate. These measurement data also served as a basis for retrieving the corresponding topographic features of the sampling points, such as altitude and segmented areas by land use types, which were obtained from the data repository maintained by the Japanese government. From a scientific point of view, we try to infer the type of the radioactive deposition process in each selected local area. Dr. Sanada and his teammates, who are also the authors of this paper, successfully categorized representative local areas into dry and wet according to the type of the radioactive deposition process. They took into account rainfall and wind data, including the amount of precipitation after the accident and spatiotemporal behaviors of atmospheric radiocesium dispersion. This long-term statistical analysis helped us find meaningful patterns in the distribution of the air dose rate in terms of topographic features. Actually, in this case, we can categorize Area A as an area of dry deposition type and Area B to wet deposition type. The dry deposition type corresponded to an area in which the radioactive material fell on terrain surfaces via turbulent flow and gravity precipitation. This means that the amount of the radioactive material was dependent on the altitude and complexity of the terrain surface shapes. In contrast, the wet deposition type occurred when the radioactive material was absorbed into rainfall and fell on the area. That it's more likely to be uniformly distributed over the terrain surface regardless of their altitude. According to these scientific insights, we can hypothesize that area of dry and wet deposition processes reveal typical patterns in terms of their torrid values, including the air dose rate, altitude from the ground, and the distance from the nuclear power plant. In areas of dry deposition type, turbulent air flows can carry radioactive materials, piling them high up in the mountain. Additionally, the amount of the material deposited was not significantly correlated with the distance from the nuclear power plant because it can travel for a long distance through the air. Alternatively, in the wet deposition processes, the radioactive material falls the ground with rainfall, and thus the distribution is almost constant in terms of the altitude. However, the possibility that the radioactive material will encounter rainfall is roughly proportional to its closeness to the nuclear power plant. Our technical challenge was to visualize a set of discrete samples and the geospatial multivariate function. In this study, we employed the continuous scatter plot as a primary tool. This tool allows us to project the distribution of the function in terms of the geographical positions onto the range space spanned by the air dose rate and other attribute variables. This slide shows the simple 1D case where we interpret the discrete sample of the function on the left to convey the underlying density map of the data as shown on the right. This representation can reveal the important patterns in the data distribution in this study. We are now ready to project multivariate data on the 2D map domain on the range space spanned by the attributes as the continuous scatter plot like this. Notice that the bright colors in the scatter plot indicate more densely projected data samples. However, in our study, we need an interface to understand the data distribution in the range space spanned by the 3 or more attribute variables. We achieve this goal by coupling 2 attribute variables and projecting the corresponding function onto a 2D range space individually. This way, we can replace the region 3 range space with the multiple 2D projections by taking advantage of the scatter plot matrix metaphor. This is a snapshot of our system implemented for the analysis of the air dose rate map. In this study, we implemented the bidirectional interactions between the map domain and the scatter plot in terms of the multiple attribute variables to investigate the relationships between them. This shows the typical example of the interaction in which we tried to identify map regions that have specific patterns on the bivariate scatter plot by painting them. Here, pixels in the 3 different colors represent such correspondences from the scatter plot to the map domain. This shows inverse projections from the gray map area onto the 3 scatter plots. This helped us considerably when we already knew the specific radioactive deposition types for some of the regions. Our first challenge was to segment areas of dry and wet deposition types by drawing the patterns specific to each type over the set of the 2D scatter plots. Here we employ the 3 attributes, the air dose rate as P, altitude from the ground as Q, and distance from the nuclear power plant as R. This consideration allowed us to identify the specific deposition types in different areas by referring to the scatter plots. Note that employ the air dose map measured on the December 28, 2012 in this case. Let us recall what specific patterns we can find for each type of the deposition process with this. This slide presents a case in which we found a potential area of dry deposition type on the map, which is represented by the colored pixels. Note that in this example, we first painted the pixels in the respective scatter plots by referring to the specific patterns for the dry deposition type. We then identified areas overlapping with the corresponding colored areas on the map. The result obtained in this map domain allowed us to confirm that area A primarily consists of dry deposition areas like this. In contrast, we located areas of wet deposition type by coloring the pixels that corresponded to the specific profiles we confirmed previously. The results showed that area B, which is enclosed by the rectangle here, is a wet deposition area as expected. Thus, we successfully categorized areas of specific deposition type by first drawing the corresponding typical patterns on the scatter plots based on the already acquired knowledge. We also investigated the temporal decrease in the radioactive level in terms of the land use types as our second challenge, but we would like to ask our audience to refer to our paper for details due to the time restriction. Okay, let me conclude my talk. In this paper, we presented our application study for analyzing radioactive deposition process around the nuclear power plant's accident site. Our future extensions include exploring more meaningful attribute values that better characterize the dose rate map and possible application to pollution problems caused by other particulate matters such as the PM2.5 agent dust, etc. Okay, that's my presentation. Thank you.